So beginning with today's session, good morning all. I'm Skandan from Mechanical Engineering Department of 2021 batch. I have Mayur from Metallurgical Engineering and Material Science of 2021 batch alongside me in today's session. So hope you guys are all doing good, doing the tasks given to you and submitting them in the forms being provided to you. In session 4 of Electrobits, that is today, we'll be covering three parts majorly. Neopixel, Microbit, and IR remote. So moving into the session without any further ado, let's talk about Neopixel. But when it comes to Neopixel, it is mandatory that we talk about Adafruit underscore Neopixel library. So it is an Arduino library that controls Neopixel and its functioning in the Tinkercad environment.
Sorry
So
for
yeah,
I think you didn't share his screen.
I am sharing my screen.
Uh,
Is it not visible, guys? Hello?
oh, maybe you can stop and start it again.
Yeah, sure. Now is my screen visible?
No.
Give me a minute.
Yes. No, it isn't.
So let me start from the first line now. Or yeah, so basically we'd be covering NeoPixel, Microbit, and IR remote in today's session. And when we're going to talk about NeoPixel, it's mandatory that we talk about Adafruit underscore NeoPixel library. So it's an Arduino library that works with NeoPixel and perfects its functioning in the Tinkercad environment and the Arduino software. So there are two things that we're going to concentrate in this definition. One is Arduino library. So what is an Arduino library? Arduino libraries are files that are embedded in the development environment that add functionality and ease out the process of, accessing an object or component basically. So what are NeoPixels? Coming to that part, NeoPixels are a series of RGB LED pixels, RGB as in red, green, blue, which are three pins internally connected to the connected to a wire. So all these LED pixels are interconnected by a single wire, all of which can be controlled individually. And the NeoPixel as a whole requires a delay for its proper functioning. And this individual addressing process requires a driver chip. So the RGB LED creates a wide range of colors based on the mixing ratio or whatever or the amount of particular color that you want to mix has to be provided as a parameter to these LEDs for obtaining various colors that you would like to have. And these are addressable LEDs. So what I mean by addressable LEDs is a new generation of LEDs that have a controller IC, basically the driver chip that I was talking about. What is the function of these ICs? These allow multiple LEDs to be accessed with a single digital pin by addressing each and the separate memory space in its RAM and thereby accessing everything under a single wire. So when we will be writing the code, we'd see that we'll be calling every single NeoPixel by its number. So internally, they have been mapped to this IC and can be called and can be given color of a particular value based on the ratio of R, G, and B that you would like to give to obtain a particular color. So again, moving on, we have the functions in this library that would be discussed before going to the code. So this is how the Neopixel ring or the Neopixel curl would look like, and this would be used in the project upcoming. So talking about the function, the first function is begin function that sets up the Neopixel object, thereby starts the functioning of the component. Then we have the set brightness function that takes in only one argument, which is the brightness or intensity of the light that the LED emits. LED as in a particular LED emits, whose minimum value is 0 and maximum value is 255. So this again points at one part or a major hint, gives a major hint that the memory space allocated for this set brightness function or the variable assigned to this set brightness function is 8 bytes and it is unsigned tone. So talking of which, I get reminded of a different thing that we'll be surprised to find that often in case of this NeoPixel library, the variables that we'll be assigning it to, or basically the integers that we'd be obtaining by assigning the functions to a particular variable. So that particular variable will belong to a data type of unsigned category, wherein we'll have only positive numbers. And again, their memory space has to be defined. So in this case, we needn't define the memory space or the amount of space that we want to give it, because we've hereby told that it's 2 power 8. But in the upcoming places, we might have to define the memory that we'd be giving to the particular variable. Moving on, we have the clear function that switches off all the pins to 0 brightness, and the function is usually at the start of the code. So this function, along with the object to denote that this is to control the NeoPixel, is given at the start of the function, start of the code as a sorry. So the next function is color function, which sets color to a particular LED by taking in 3 parameters. First is the amount of RGB. So basically the red, green, and blue that is to be mixed to obtain the final color. And this final color is encoded as a number that occupies 32 bits or 4 bytes of memory space, meaning the values can range from 0 to 2 per 32 minus 1. So again, this is what I was talking about. And in the code, you would be seeing that the variable that we assign this color function to is a 32-bit number, that to unsigned. So that's why we have this from 0 to 2 per 32 minus 1. Unlike the case of int that you would have seen in your C program that will be having 2 power 8 again, as in from minus 128 to plus 127, which is a different case. I mean, that wasn't int, that was character, my bad. So moving to the next function, we have set pixel color, which takes in 2 arguments basically. First argument being the pin number and the color value from the color function. So this is the function that sets color to a particular pin. That is the function that gives the output of the color that you want. So this function takes in its second argument as the number or the variable of data type whose memory space you have defined in the first place, which we'd be seeing in the code after some time. So this set pixel color sets color to a particular pixel in strip, as I was saying. So then we have the show function, which the value set by neopixel.set brightness and neopixel.set pixel color, which are the second and fifth function, will take effect on the NeoPixel once the code is run, only if you put the show function. So this is added at the end of the function code. So basically, we writing functions as in the real programming language function to ease out the size of code. So in that case, when you put all the set brightness and set pixel color functions, at the end it is mandatory that you put show function, which again glows up the Neopixel depending on whatever conditions or set of parameters that you set for them. So, and yeah, finally, at the end of all the Neopixel operating functions, it is mandatory that you mention the delay time also. As I said in the first slide, that delay plays an important role in the proper functioning of the Neopixel. And that makes it a characteristic of Neopixel that you should mention delay time. And we'd be seeing in the code that the function has a delay time. And yeah, we'd be seeing a few more characteristics while going through the code. So yeah. Let's move on to Tinkercad and tinker the loading sign with Neopixel. So as usual, we'll begin with taking Arduino. Then, as I've shown you guys, the Neopixel, take the pen for them. So there are different sizes, and in today's session we'll be discussing about the largest of them, which is 24 pixels. You find that there are two ground pins, two power pins. So if they're directly connected, the region can be crowded over here. And then we'd be using the input pin, which gives input for this to be used to glow up according to our accord. So, and yeah, to have not have a traffic in this connection position, we'd be using breadboard. So let me give power to the breadboard. So yes, as per the breadboard connections, this set of pins have now received 0 potential, and these set of pins have received 5 volt potential. So now let's move on to connect the ground to ground. Now we have to power the Neopixel by connecting the power pins on the Neopixel to the breadboard's power line. Finally, I'll just color code these the wires so that it looks proper. And finally, this needs to go to a digital pin, which can be one of these from 2 to 13. So let me choose pin number 5. Give it a color code of. Is the pace fine, guys? Like, you're able to understand the function, Yeah, I'll be covering the arguments once again when I'm going to write the code, as in right now in a few minutes. Respond with thumbs up if at all you're able to understand the code, the setup so far. Maybe I'll show you the setup also. Okay. Connections once again. Sure. So we began by taking the Arduino board. Then we took the Neopixel of 24 LED pixels, which is the largest one among them. Then we saw that in the Neopixel we had two ground pins and two power pins. We'd be giving input to the LED. So we chose to connect the input to the digital pins on the board, which are 2 to 13. So you can connect it to any of the digital pins. Then coming back to the ground and power part. So basically ground can directly be connected to ground also. And the power and power part can directly be connected to the power line as in the 5-volt thing also. But the problem is it will look much crowded and the NeoPixel has to be brought to somewhere here in the real life. So in order to avoid that issue, I took a breadboard wherein you have multiple, more than one connection points or basically functioning as a junction box in real life. So I connected the minus sign, which is basically the lower potential to ground and higher potential to 5 volts. Thereby, we'll have these set of pins to be at a very high potential, very high as in 5 volt, and the negative set of interconnected connections to be at zero potential. And then connected those zero potential to ground of the NeoPixel and the high potential to power pins of the NeoPixel. And only one power pin. So basically, one power pin and one ground pin would disable the functioning of few of the LED. So if you need the functioning of every LED in the strip, we need to connect every pin to the ground, as in every ground pin to the ground and power pin to the power, or else every LED that we aspire for wouldn't work. Which is again all the 24 LEDs won't work. Okay, so moving on to the code. We'll first have to include the Adafruit library, which is again the place where we have or we can control the NeoPixels function. Yeah, have a eye on the function's name, guys, that the P is capital. Missed out every time when I used it, so don't want that to happen with you guys. And then we need to define two names or two variables. So basically the pin number in which this thing is connected. So let me name the pin as P. So the digital pin through which we're going to give input to the NeoPixel will be named P, and similarly the number of NeoPixels that we have taken, so basically which is 24, and those are the number of pixels that we want to work with. So that is also that may be given a variable name, let's say L and 24. Yes. Now, before going to the void setup, which is again beginning the NeoPixel and looping statements, which again would repeat one after the other according to our desire when we click on something. So that before going there, we need to define something called as the object now. Which is again characteristic of libraries that we have been defining. So Adafruit _ NeoPixel. Let me call the NeoPixel ring by the name H. So let's say even strip that works. Adafruit pixel. Now this function takes in 3 arguments. First argument being the number of pixels, L. Second argument being the pin to which your NeoPixel ring is connected. Finally, the third argument, which is the color argument or the set of colors that you would like to use. So neo underscore grb. So there's a specific way of writing these 3 colors. Why am I writing GRB instead of RGB? I'll show you in the code that if I write RGB or BGR or BRG, there can be changes in the colors that you are going to get. So this is a specific way wherein when you're giving the color input, basically, you will be writing it in the order RGB. For that to happen, you have to define this in GRB order. If you instead write RGB here, and again, expect RGB to be the order of the colors, that wouldn't be the case. That's the problem, or that's the characteristic of Adafruit Neopixel. And I'll be adding it to neo underscore khz 800, which is basically the rate at which the change in color has to occur. It has to occur in 800 kilohertz, or it can be 400 kilohertz, which are again two fixed things in the Tinkercad and the Adafruit. So they are characteristic values again. You can't change. So in the setup, as we discussed during the functions, we need to define script dot begin function, which doesn't take any input in it. While coming to the looping statements, we're going to give only 3 statements. As I told you that we'd be operating the colors and basically assigning the colors also by separate functions in the code. So let us go to the function before coming to the loop, which is, in my view, a better option. So let me define void, because we're not going to return anything. Just going to alter the colors in the Neopixel directly. Code loading, because let me let loading only. U in 32 underscore C. So what it basically does is the parameter that I've defined creates a memory space of 4 bytes that takes in unsigned integers, basically any positive integer between 0 to 2 power 32 minus 1, and assigns it to C. So as in a memory space is created of 4 bytes, and it takes in, and the memory space is named C, and we'll be seeing in the code that where we're going to use it. So basically, this is a kind of data type that are very much specific to functions like Neopixel, and yeah. So these are really specific data types that we won't be using generally. Why is it being the case that we don't use it generally? This is again data type of data type which is intermediary between int and char. Why is that so? Because we're here the uint x, you can define the number of bits that you want to define, or assign to a particular data type, and thereby you can alter the memory space that you're going to that your object is going to occupy. So it's not completely going to occupy the 4 bytes. As in our case, we have directly used 32 bits, but it can also be a value between 16 and 32, or even 8. So it can vary from 4 to 32, basically, according to our record. So we basically know that this value will have to occupy this amount of memory space. Then we can directly go on to assign the value. Going on the function code, we'll have again another this thing, whose memory space, maximum memory that it would require is known. And well, that's obvious too, because you will be having a double. If at all you double this, or in a span of into 10 into power 10, you'd get this number. So yes, that is again a valid argument. 10 to 10 as in how may I put it? Into 2 power 10 repetitions. You might find that this would be enclosed in a u int of 2 power 30, basically 0 to 2 power 32 minus 1 range. So this can even be reduced, but cannot be reduced to very bad extent that we can expect. So that's why I've given this value. Yeah, so why have I given 28? So there's a reason that why I've given 28. First of all, the loading symbol that I have shown you in the slides had 4 dots. So for that reason, we'd be using 28, which is again 24 plus 4. Second reason is that second reason as in this can be altered. So let's move on to the functions that were discussed in the code. The slides there. Just set pixel. Oh, that was small. Set pixel color. I set the first one to be 0. So as it moves, the pixel before it needs to be 0. Script dot set pixel color. Now again, the pixels following or in the backwards direction. So we are this pixel. So the pixels following it need to have a particular color that we're going to assign. So yeah, that takes in the input of. Finally, script dot show. So we're done with the changes. So we're giving the show function. Finally, we also be using, oh, okay, problem with last class too. So I don't want to repeat. We'd be giving the delay for the proper functioning of Neopixel. Let's say it's 2. This needn't be 250 only, but then if it is not, the delay is not given, the Neopixel won't work because it's a characteristic of Neopixel to take input of delay for its function. Yeah, we're done with the functions that we're going to use, as in the only function here which is load. There can be more than one function depending on the number of Neopixel and the way or the number of colors that you want to see. You can even try it out, try the rainbow color loading symbol. For that, you have to define another function which again randomizes the color. So writing the function that we're going to use, we'll again be taking the input of set color, which is again strip color. Again strip dot color function, which again gives the input of color. So I want the 4 colors, basic colors that we saw in the Windows 7. So that was again a Windows loading screen, no? So we'll go by the convention only. First color was red on top left corner. Then it was blue if I don't towards the right. Oh, this is green. I went. RGB. So let me get 2045 here. We'll give a special color as in which is not one among those in RGB. And you would know that at the end that this is not a very different color. Basically, we're going to mix green and blue in the whole thing and some part of red. So which will be somewhere in the range of green. Very much in green, but then yeah. So let's move on to the simulation and check. Maybe yeah. Is the code understood, guys? Basically, KH is the 800 means the rate at which. So KHZ is the kilohertz of data transfer rate, and 800 is the a number of as in what do you call it? 800 KHZ rate is the data transfer rate from your internal controller IC to every LED. It can even be 400 kilohertz, but then for a faster, color change that you would like to see, which is by the show function only. You're having this thing at the last of your code. So that again allocates memory to your particular variable that you have defined. So, and yeah, specifically talking about u int underscore t, it's unsigned integer variable in the range 2 power x minus 1 to 0. So basically you can use any number between 0 to 2 power x minus 1. But the thing is, it's not completely an integer. So we don't want to use the memory space unnecessarily, and we don't again want the variable to take any negative value at any cost. So that's why we directly using uint, and we're also using the memory space allocated to it right after the int function. So shall I move on, guys, or are there any doubts that have to be discussed? Basically, the data type is used for two functions. One is we don't want to waste memory space. Other is the case that we don't want the variable to take any negative value at any cost, because that would again cause problem in your pixel, that because it takes only positive values. Number of LEDs. Well, it wasn't the case that we don't we didn't use it for the number of LEDs. LEDs were defined here, right? You mean this part? This was for again the set pixel color function, wherein again we'll be using, we need a number between 0 to 2 power 16 minus 1 range. That's again different. This I is less than 24 minus 24 plus 4 was assigned so because we'd be using the four LEDs for the loading symbol to properly be shown on the LED set or the LED ring. So other than that, yes, there's no function for it. We've given just a memory space here, so that works properly here. So here again, we need to have this much amount of memory to be assigned to the first argument. That's where we've taken this. Or else, you can also do it with int, but then that would cross the memory space that you would be occupying or assigning to the first argument of your set pixel color. So for this function's proper functioning, we have taken this thing. Or else we don't even need this. It's again, you can even define int, unsigned int, but that might cross the memory space that has been allocated for these parameters. So in order to ensure both, we've taken it. And again, 0 to 228 can be cased in char also, which is again very much less, as in it can be from minus 128 to 127, which is 2 power 8. So basically it can be 8-bit digit also, in which you take the input, which again within the range. So it doesn't matter. But we have taken it so because we again want to use the maximum space for this function. Maximum space as in we initially we didn't know that we'd be using 28 is when we assigned, and now again when you're sure, I guess we can use char also. Guess that doesn't matter. So can anyone spot the error in the code or the mistake in the code that I've written? There's a subtle mistake. But I told it while making, mistake. But then it wouldn't have been a mistake if at all I've told it a proper. The mistake was we want the four the four colors to move in front. But unfortunately, I mapped it to the backward direction. So I told that when your this thing is zero, the colors would go in this direction. But actually, the loading symbol is in this direction. So if it's in this direction, every other pin in this direction would also get it because it's going to move in. I mean, the pin is going. The what do you call? Colorless pin is going to move in this direction. Every other LED pin in this direction would take the C value that we're going to assign, which is not in our favor. We need our colors to move in the front rather than the uncolored part to move in the front, which was the case too. As in the uncolored one was moving in the front. So we see that this uncolored LED is confirmed, I mean, advancing, but then the all other colored pins are again not being. You find that even they are four in number, they are uncolored things, but then the others are increasing number. So we want the exact opposite to happen. So we'll go to the code, change those four things to C and all others to 0. So we'll find that exactly the opposite thing happens. And then four of them will be colored, and that too of the color that we told them to have basically red, blue. Special color I was talking about. It's again not possible with the customary LED. Finally, your yellow. And that again, this yellow's intensity can be changed as in the extent to which your yellow color is being shown. So is the code fine, guys? Yeah, sure. One minute, I'll zoom out and show the output again. Not 8, it's 800 kilohertz, if at all. This thing is showing in a way. It's not 1, no, it's L. Because we have used it in the third line as a variable that is being given or parameter that is being given to the function to define the object that is being used in every part of the code. So I guess that's L and we've written 1 in the code again, I mean, the chat again. So it's the code and the setup understood, guys? Respond with a thumbs up if at all you understood the code. Hoping that it was understood by everyone. I mean, I've got some responses too. Thank you. So moving on to the slides. I've even provided the code here, slide. So if at all you find any difficulty in writing or again you made mistake somewhere, we can again use this. So next up we have the microbit. So microbit is a pocket-sized computer developed by BBC to demonstrate how software and hardware interact with each other. So it was developed for educational purpose. It has LEDs and many input output components that you can see. You have the pins, you have your ground pin. I mean, yes, not visible because of my this thing. And what it provide? Would provide. Yeah, you have the 3-volt input supply pin and then ground pin. You have even buttons on the board. Um, Other than this, you have few more functionalities available with your microbit that makes it very much versatile that it can replace even your PSPs and compasses too. So, and yeah, very much importantly, it's an ARM based embedded system. What is that? So You've seen that Arduino, I mean, you've seen Arduino and Tinkercad, right? That is Atmega based embedded system. This is again ARM based embedded system, which was there in one of the quiz questions that you have ARM Cortex N4. Exactly, the same ARM Cortex N4 has been used as the embedded system for your Microbit. It was developed by the Britishers for the educational purpose to show how the computer would interact in all circumstances almost. So each of the 25 LEDs that you're able to see here, so we have 505 LED matrix. Each of the 25 LEDs are individually programmable and can display animated patterns and arrows, which again would be used in our upcoming project, and scrolling text. So this is a functionality that is really cool, that you have scrolling text functionality. If at all, you can imagine that we might have one which can be shown using these set of pins like this, two which again can be shown like this. But what about 10? So we have a scrolling text functionality which enables a particular set of pins to be, after one gets displayed, if the pins would make the one appear to move towards left and then show the zero. So that's again a cool functionality, I guess. Then we have Microbit, as in Microbit programmable buttons. So the controller can detect if the button is pressed or not. So how's that helping us? This can be programmed according to our record. This can be this, as in the microcontroller then can be used to make game controllers or control music. So basically, when you're, I mean, even what do you call, a head earphone can be made with the microbit. As in when you click on the button that, I mean, to move on to the next song, you can click on a button, and then to come back to the same song that you were previously playing, you can click on the other button. So you have two programmable pins too. I mean buttons too. You have an inbuilt compass, and which is again a 3D magnetometer that has a sense to detect direction. And the second most important function is to detect the presence of metals and magnets in its nearby vicinity. So directly the microbit can be used to detect metals too, rather than using a metal detector, which is again a different whole sort of different device. You can even use a microbit to detect if there is some metal or even metal ion caging device nearby. So, and yeah, you have three input output rings along with a power pin and a ground pin. So each of these input output ring pins, I mean pins as in the rings, you have a pin, a very small pin set up at the end of these three input output things, which can be either analog or digital in their functioning. So what would the microbit do? Whenever a component is connected through a wire to these pins, it reads values from the sensor, as in the component, and acts on them. So it basically can take input and again give output, as in give input back to the sensor and make it act according to your will. Other than this, you have a 3-volt power supply, and you will find that in our code we'll be using a component which requires more than 3-volt power supply, and still it can be integrated with our microbit to, as in, use the component. So basically, it's not the case that it can't supplement another power supply. It can supplement another power supply in making a component function. So basically, it can act both as a power in giving in power delivering board, as well as a power supplementing board. So this the ground pin of your microbit can also be accessed for that purpose, and which we'll be seeing in the code upcoming. So it has two more very great functionalities, or breakthrough functionalities, which I can say that makes it really different from Arduino. So it has on-mode motion detector, which is again a 3-axis digital accelerometer that can detect movement and even measure the acceleration along X, Y, and Z axis. It also has Bluetooth feature, and possibly it can even have as an, now I guess it has been integrated recently, a Wi-Fi board or Wi-Fi chip, which makes it easier to connect to nearby devices. So, and then function as, all these things that I've told. So you can control even a game on your PS4 or PS5 using the buttons over here. And even the motion sensing can be done appropriately to control your game. So let's move on and see a bit of functions that we'll be using in today's code. But I'll not be talking about these right now. So as in, we'll be talking about these in the code directly. But yeah, here I've put it for a reason, as in for the slides itself of about the functions that we'll be using in the code. But then here I would like to mention two things that we'll not be talking again and again in the code because these are repetitive. You've seen that basic is given at the start, pins are given at the start. So uh, we'd be using again in the Tinkercad, but this time it's not JavaScript. Unlike Arduino, it's not JavaScript. We'd be using a programming language called MicroPython, which is much similar to your Python programming language. That the functions are functions are given after your this object on which the functions are going to act. So basically, before the point, whatever has been given, basically your object has been given, object on which these functions can apply. So basically, basic is an inbuilt object of the language that pertains to your microbit board. So pins are inbuilt object that pertain to your input, what do you call it? The pinholes, basically, that we saw in this thing previously. So these pins can be accessed by giving the pins object name. And we can be using a servo motor that's being connected to these pins, or you can take take analog output, or even give analog input, which you'd be seeing in the code. And then we can take input of, what do you call it? The compass, inbuilt compass or the inbuilt magnetometer that is within the microbit by naming the microbit object as input. So let's move on to the Tinkercad code, wherein while defining or while programming only, I'll be discussing about all these functions. Let me take a different window of this thing. So this is a controller board of itself, so we'll be not using our Arduino. That fact. Then we'll be using a servo motor. So yeah, the project is all about your servo motor that functions or shows the points in the direction that your compass is going to point in. This is the ground pin. So yes, can be connected directly to the ground. This is a signal pin that I guess you can connect it to any one of these three pins, but then I choose to connect it to your second pin. And yeah, you see that your servo motor requires greater power than 3 volts. So what I'll be doing is use the, yeah, you can directly use the 9-volt battery. I'll be using 1.5-volt battery. So it's fine even if you use the 9-volt battery. Which gives a greater power input to your servo motor. or you can use three 1.5 volt battery, which again serves our purpose, but then here we need to connect each one of those in series to get the output. So I thought of taking the this thing directly. So yeah, you can use one basically the servo input that we require is 4.5 volt. So it can even be 9 volts if at all that doesn't cause any problem to a servo. I don't think it does if we are going to use a resistor in between. So let's move on to the code. So yeah, first thing I'd like to define is your angle. I mean, let's fix the angle at the start of a function to be 0. And yeah, you don't have to give semicolon after a statement because it's Python. I mean, language very much similar to Python. And on forever. So not a compulsory what you call name that you need to give to your function. But then this function is, I mean, the name of the function is very much implicit. That basic dot forever is the loop. I mean, this function basic dot forever is a looping function that tells your microbit to repeat a particular function, and I mean on and on and again. So you're giving this name on forever in order to imply the fact that this is going to be given as your function input function parameter inside your basic dot forever function. So basically, this name implies the fact that your whatever, I mean, wherever it's going to be used, it is going to repeat forever again and again. So you can even change its name to, O, F, or I mean, a single letter word so that it's easier for you to even write the code. But I wish to have it the same way that, as it is. So yeah. And yeah, you need the angle to change when you're even accessing it outside. So basically, you're accessing the code, I mean, function outside, no? And during the processing, we'll be changing the direction of your microbit board. So I guess it's better that we define it as a global variable rather than having it 0 all the while once it is changed. And yeah, unlike your Python, how is it different from Python? You directly have your math functions available rather than you don't have to import your math library for accessing the functions over there. And yeah, you just have to give your library's name, and then I mean the since the my math library is always built in, you just have to give the name of your library and dot floor function. Why are we going to use floor function? Because we basically have 8 directions that can be shown by a compass, and when you're going to mimic the same characteristic over to the this thing, what do you call, to your servo motor, you need to have only 8 direction pointing uh, values. So basically, we'll be using only 8 values. And how are you going to get those 8 values? So again, this function input uh, compass underscore heading shows the direction in which your microbit controller board is pointing in, and take that angle to the reference direction and give that as output to our function as in the programming language. We'll be adding 22.5 to this thing, which is because in case of 0, we need to have 22.5. And in case of 22.5, which is again your northeast, or I mean, I guess, yeah, northeast direction, if you consider 0 to be your north, uh, we'd be having 45 now. So let us divide this by 45. Divide as in the complete set of value, complete value by 45, so that we don't have any problem. As in, you want your north to remain north until this value. So whatever values come before this would take your northeast, and by giving 90, I mean math floor of 1, it will go to your right direction, or what you call your east direction. So if at all your angle, yeah, waiting in the lobby. Okay, no, it's not a problem. Are there any doubts until now, guys? Is the connection perfectly fine? So if the angle is equal to 1, I mean, yeah, angle is 1. Sorry. Yeah. We want the object to show as in, so yeah, this is a function that shows your arrow. So basically, whenever a direction is, I mean, yeah, direction is detected, that has to be shown in your display was what I was saying. As in, how will you know that in which direction is your compass pointing? Yeah, yes, that you would be getting a, kind of a simulation here that tends to rotate your board. But how can that be implied on your this thing in case of your real world application? So in order for that to happen, we'll be showing your direction in which your this thing is pointing. I mean, microbit is pointing on your display, a 5 into 5 LED display through this function. And again, the input that's being given to this thing is again arrow names. So this is a special object given, I mean, assigned to your all set of arrow names so that you can access your northeast direction or any direction for that matter. So whenever you're going to type an arrow direction as input, you have to call this object, which again converts it into another data type that is you know acceptable or can be taken in as input or given as input to your this function. An advantage with your this thing, MicroPython over your other languages is you have elif condition, which again facilitates you to reduce the number of else if or looping else ifs that you're going to use. So let me just copy paste this. But in the second case, we'd be having a different direction, which again only east, right? So when you're going to have your 45 over here, is it 45? And so whenever it's going to cross your threshold value of 77.5, I mean 67.5, you should have it as east. So basically from this direction should be your north, I mean east. So yeah, again moving on, I'll just keep copy pasting this code, this part of the code again and again so that you don't have to change things. I mean, we only have to change things. So this thing becomes southeast. It becomes south. This is southwest. West. Northwest. Else under any condition, we'll be having north. So we need to mimic the behavior on your this board, microbit controller board's display onto your servo motor. I mean, the particularly the direction that we have assigned so far onto your servo motor. So let me take your a variable whose data type need not be defined again in your MicroPython as the value that is being given as input to your compass. I mean, input by your compass. And why are we taking it now explicitly? We could have just given it as a parameter to your servo function that we saw directly. Yes, we can do that. I'll show you the problem with what happens when you give it so. Well, I'll move this thing a bit. I mean, as the simulation is being shown right on the servo motor, I'll move the servo motor to the left for the code also and start the simulation. The thing is, when you click on this, you can directly access your compass directions. And yeah, oh my God, it's not visible. This thing is not visible. Yeah, now it's visible. So when you try to change the direction of this turns in the opposite direction, but then this rightly points in your compass direction. So when it crosses a particular value, it shows to the right. And again, when it crosses a particular angle, it shows in this direction. And again, when it shows in this direction, which is again around the range of your 160, I mean 155.5 to 180 range, it shows the perfect time, 157.5. And again, in this direction, the displays are all fine. But when it comes to the servo motor, it rotates in a different direction, as in right opposite way than we expected, right? And that too, basic functionality that is available with your servo motor is it can rotate only between the angles of 0 to 180. So what I'm going to do is change the code slightly, very slightly, in a way that it is able to mimic the directional change, at least for 180 first. And then I'll change the code once again so that the other side of your pointer will point in the direction that is required. So let me show it rather than saying through words, let me show it through the code. So until 180, it has to move in the opposite direction than our favorable direction. So it was rotating in this direction initially, while this was showing the direction in this direction. So basically for a rotation of this kind, it is rotating in this direction. I mean, for a clockwise rotation, it is rotating in anti-clockwise sense. So we want it to rotate in clockwise sense. What I'm going to do is assign i's value to be 180 minus I. For a case of 180, I mean 0 to 180, now everything will be sorted. Let's begin our rotation. You'll find that the servo pin rotates rightly in the direction that we wanted it to. But once you reach 180, it's again rotating in the opposite direction to the rest state, which is not again a favored output that we wanted. So let's move on to the code and alter it for the case of 180 to 360. What I wanted the pin to do is, rather than going to the normal state, I'd like to continue it rotating, but that won't happen. So I'll change its direction of motion as in now the opposite, you know, half pin or half servo motor thing or half servo object would now point in the right direction rather than this pointing in this direction. This part of this thing. of your servo motor would now point in the direction that is required, which I would do by subtracting 360 from my display. Now again, everything's perfectly fine. When we rotate it to your 180 until your 180 degree, it goes by your 180 minus I function. Once we reach 180, this will turn and this part of your this part of your servo motor pin would point in the direction that we require. So it's pointing in 292. Now again, it will rotate back to your normal state. And now the upper part will now again point in the right direction. So yeah, finally talking about your servo function. So what it does is it will write the value, a particular value and the pin number which has been assigned here as analog pin or P2. Why is it written analog pin? You want your pin to act like an analog pin, that it takes values between 0 to 360 that is being given as input through the object or a parameter that is being calculated for the value of the rotation previously and then given as input, second input to your servo underscore write underscore pin function. So yeah, guys, any doubts? Okay. Uh, yes, more than responding on the forms, polls, can you guys start asking doubts? Oh my God.
Skandan, can you please share that code in the chat?
Sure, yeah. I'll share the first code also.
Yeah, yeah. If possible, share in WhatsApp as well.
Okay. So I'll go through the code once again. I will tell through the code. Initially, you want your pin or angle at any cost to be in the north direction. And that is your case with a microbit also, which again starts from north, which is 0 degree. So basically, we'll be changing the angle through your function, throughout your forever loop, which is again the looping statement of microcontroller microbit as a controller microbit. And that's why we have given it the global assignment, which will say update your value again and again within the function when your change is outside the function. So that is not the case that is usually observed in any programming language. For that to happen, you need to give a qualifier. So basically that qualifier in our case is global, and in case of Arduino was static. So then comes your angle function, angle variable, which is again of the which is again a value from 0 to 6. So initially it is always 0. When its value is 1, you need it to point in the this direction. You need your values to change in the all 8 directions. Sorry, not 6, 8 directions, beginning with 0 to 7. And how are we going to get those 7 values? Based on the rotation angle. And how are we going to get the rotation angle? That we're going to get by a function that is input dot compass underscore heading, which again shows the direction in which you're heading, as in the microbit is heading. So its value is retrieved, and you're going to add it to 22.5 and divide by 45, because in case if you're going to have 22.5, which is your northeast direction, I mean, northeast direction, no, when you're entering the northeast range, which is 22.5 to 45 plus 22.5, which is 67.5, you want it to point in the northeast direction. And in the range of minus 22.5 to plus 22.5, which is basically 360 minus 22.5 to plus 22.5, a 45-degree range. You want it to point in the north direction, which is given as the last thing. Point as in show the pointer direction on the display screen. And that is the case with every if-else statement, where you're going to retrieve this angle's value and compare it to every single integer. How is it being converted to integer value? Unlike your normal this thing, what do you call a programming language which is based on Java or C, you would where be defining the data type of your angle, so you won't have any problem. But then here, when you're just going to divide the values, you're going to get it in float, and then it's not going to be returned as an integer. And when compared with an integer, obviously this will be qualified to a value that is not perfectly an integer. So basically, there will be discrepancies. Now to avoid discrepancies, we are using float function, which is exactly your greatest integer function of mathematics, that is being used from your mathematics library, used in, which is inbuilt in case of your MicroPython, unlike the case of your Python, where you have to import the library, or even in that case, Arduino, where you're going to import. I mean, we have imported your Adafruit library, which is by inclusion. You don't have to even mention that is being included, because you're directly using your math object, which is again here it's not directly an object, but it's the library. That library that is being called as an object. I mean, what I meant by not an object is you're going to call a library by its name, which is again an object for this particular part of the code, but then in reality is a library. Then we're going to compare if the angle is 1, which is again, it's in the range of 22.5 to 67.5. It will be northeast. And from 67.5 to 90 plus 22.5, 115.5. It 112.5, or yeah, 112.5. It will be in the northeast direction, which is pointing this way. And again, after a gap of 45, it will be pointing in this direction, which is again the southeast direction. Again, we'll come to the south, which is again a clockwise angle assignment. I mean, angle to number mapping that I've done in the code hereby. And finally, when it came to the reading that I'm going to give as input over here, I need to modify it a bit for when it's going to give it as an input to the servo motor, because there are 3 things that I have been addressing. First thing is, when you're going to pass it directly, you won't see a change only. I mean, you won't see a change as in you won't see a change in value after 360. First problem. Second problem was it was rotating in the anti-clockwise direction, although we were traveling in the clockwise direction when you twisted your microbit. So in order to address that problem, I brought in your condition of I is less than 180. And yeah, the third problem was servo can rotate only from 0 to 180 degrees. So until I'll mention it here that until, oh, I have to stop simulation. Until here, it is your one head of the pin that is pointing in the right direction. So in the I less than 180 range, this pin will point in the right direction as the compass. And if I not write this part of the code, the pin will stop functioning because it can't go from values greater than 180. This was given 180 minus I because we wanted it to go in the opposite direction as the direction it was, accounted for. So basically it had to move in the anti-clockwise direction, but now we want it to move in the clockwise direction, as is the case with your this thing too, because we are moving from north to east, then to south, and then to west. So finally, from this point, we needed to continue, but that can't happen is what we know. So what we did was to make your other head of the pin move in the required direction. required direction. So I'll copy this code maybe because it has documentation also. Required direction. Rather than your traditional this head of the code. And yeah, finally, we have given this looping statement, which again makes this part of your, this whole function repeat over and over again so that we are able to see the changes in the values with changing of your compass needle. So hereby we are retrieving your this thing, retrieving your number mapping to your direction. Yes, now it's a bit more clear than what it was, math.floor function. So basically, it's a function that converts whatever argument that is given inside your brackets to the nearest integer that is less than or equal to your previous value. As in, integer close to your number means a different thing, but then number less than or equal to your number, as an integer less than or equal to your argument given inside, is the definition of floor function, which is basically the greatest integer function of mathematics, which is being used as with a different name called floor here. Send this code in WhatsApp. Yeah, I'll send this code in WhatsApp.
Yeah, it's sent. No problem.
Oh, it's sent in WhatsApp.
Yeah.
I'll just send it here also, as in with the documentation. If possible, you can delete it, or maybe yeah, delete that code and then send this code.
Yeah,
and I'll
sure.
also send the previous take a cat thing.
Yeah, else you can share this.
So yeah, till then, I'll share that code, and now for now, I'll stop presenting and we'll move on to the IR remote part with Mayur on dais. So yeah. So now yeah, Mayur, you can take the session.
Is my screen visible?
Yeah, it is.
Yeah, okay. Yeah, so most of you will be before starting, myself Mayur, and I hope you enjoyed the session till now. And now we will discuss one of the most this is the most common way of communication you use daily. Like the TV remote you use is based on IR communication, that is infrared communication. The more gadgets which use this type of communication are motion sensors, DSLR cameras, etc. So yeah, moving on. So IR communication consists of two parts. It has one transmitter. This is what it is fitted in your TV remote, and this is a receiver which is fitted in your setup box or whatever. And this is uh, this is indeed a LED. Like it is a simple LED with just emits light in IR region, which has wavelength greater than the wavelengths in visible region. You would have know that what is IR region. So IR region is just the spectrum of light next to visible region in terms of wavelength. So it has wavelength greater than the wavelength of visible light. So you can watch this. You generally can't see this with your naked eyes, but you can see the IR remote flashing it. Flashing through IR light flashing through it when you see it with a mobile phone or a tablet. So yeah, so what actually happens is this LED emits the IR signal which with a particular code, and it is received by this transmitter, and this is this is a receiver, and it is decoded and sent to whatever device you want, and the device manipulates on the data we get from the transmitter. Yeah. So now actually there is much noise in environment, like the sun, the sunlight, the any form of uh, uh, any object also emits radiation, like by Kirchhoff's law. So there are many sources of IR radiation around you. So if you are sending your IR radiation, your IR signal in such an environment, it may interfere with the signal you send with remote, and your device may not get the IR signal which is like you want to send. So to prevent this IR noise, there is a encoder fitted in the transmitter, which converts the binary signal that we generate on pressing the button on the remote to a modulated voltage electrical signal, which is then emitted. This electrical signal is then emitted as modulated IR signal by the IR LED. This is again received by an IR diode, which demodulates it back to binary signal, and it is like sent to device again. So unlike Bluetooth and Wi-Fi, this modulated IR signal cannot penetrate the walls of your house. Also, like you would have like gone into fight with your family members, like when you stand in between the remote setup box and like watch TV, and they are like clicking their remote, and it is not working. So actually this requires a direct line of sight, like the remote and the this the this this LED and this diode must be like there must be some a line connecting these, so that the signal is received, so that it should not be like something is interrupting in between them, and you are like pointing LED somewhere else, and your set-top box is in some another direction. No, it will not work. You should like, there must be direct line of sight from this to the receiving IR diode. So going on further, so now there is a particular protocol which is followed by IR remotes, and it is nothing but the pattern in which modulated IR signal is converted to binary signal. So the modulation is like done by generally a 38 kilohertz frequency, which we known as which we tell as carrier signal, and this signal is generally like by scientific studies, it is seen that this signal is generally less available in nature. So because of this, we mostly use 38 kilohertz for modulation, 38 kilohertz signal for modulation, and by this, like your receiver knows that it is being transmitted from a IR remote and not from and the signal is not received from the environment. So there are many protocols like Sony, Matsushita, Matsushita, NEC, RC5, and this is the typical way in which NEC protocol works. So the binary logic 1, so that high is sent with a high pulse of 38 kilohertz signal for 562.5 microseconds, followed by a low pulse for 1687.5 microsecond. And for logic 0, it is the 38 kilohertz IR signal is kept high for 562.5 microseconds and low for 562.5 microseconds. So these other communication protocols like Sony, Matsushita, and RC5, they just differ in the time for which the IR signal goes high and low for a particular logic, like binary logic for 0 and 1. So that's difference between IR transmission, that is different, just the difference between these uh, communication protocols. So yeah, so when you press a button on remote, you generate a binary code, which is binary code. You can say it is a hexadecimal code corresponding to what you press, and it is modulated and sent over the IR receiver. Now the receiver receives it and decodes it and send it to microcontroller. So I'll show you just the simulation that how does it, like how do we get a binary code corresponding to a button pressed on IR remote. So let's move on to Tinkercad. Yeah, so are you guys following till now? Put yes in chat if you are following. Yeah, any doubts till now? Yeah, okay. I take it as yes. So let's move to Tinkercad. I'll post you I'll just post you a code which you copy and paste, and first we'll build the circuit. First we'll build the circuit. So this is what the circuit we will build. Like it is just very simple. Just check one IR sensor. I'll show you where it is. Take a Arduino and a IR sensor. Search IR sensor. You can take this out and put here, and also you can take one IR remote and also drag it and put it here. And just you once go through the pinouts of this. So this is the power pin, this is the ground pin, and this is the output pin, which sends the binary signal to the your microcontroller, that is Arduino. So uh, put yes in chat if you are done with the if you are done with this circuit. Or I'll wait for 1 or 2 minutes. You have to just mount these 3 wires. Yeah, I would have sent you a code in chat. After you are done with circuit, just copy paste it in your Tinkercad code, and okay, I defined sensor pin as 7. In WhatsApp. Yeah, sorry guys, I disconnected. Yeah, are you done with it? Can I move on forward? Yeah, okay. So now I'll just explain this code. Uh, this is the library we need to call for using these IR uh, commands, and we are like this line just defines the sensor pin as 7, and this line just creates the object for IR receiver, and this sense, and it also signifies the pin number to which it is connected. Also, will address the decoded results as commands. Okay, so in void setup, this we will be just for this we will do for initializing the serial monitor. Then IR enable IR in. So this we will do for initializing receiver for receiving the IR signal. Also, this function does the work of blinking the LED on Arduino after it receives a IR signal from transmitter. So yeah, in void loop, if what does now see if IR dot decode and percentage commands. Now in if statement, if you like detect some IR some IR signal, then this will take some value, and which implies that uh, it is not, if it is non-zero, then it is always true by the syntax of if statement, and if this if statement goes true, which goes true when you receive a IR signal, it does print the value of command in hexadecimal. After that, we'll delay a bit so that it doesn't go printing. Like if you press it, like it will go on printing 0xFFFFF, which means that if you remove this delay, I'll show you during simulation. We'll include this delay. I'll tell the reason after that while simulating, and then we'll use this command to reset the IR receiver and make it ready for the next uh, next command, that is next transmission to be received. Okay, so are you guys following the code? Have you understood the code? And percentage sign is for like address to which command is stored. Would have learned in C programming, right? I hope it is clear. Yeah, those who didn't understand code can like ask the doubt if you have any. Is it understood? Well, I hope you understood it. Yeah, I'll move on further. So we'll simulate this once. Yeah, okay. So we'll go to serial monitor. You can ignore the message it comes first. We are like just interested in hexadecimal value we get for each click on the button. So when I click this power button, it corresponds to hexadecimal value FD00FF. Similarly, for voltage, it is some other, and for function, it is different. So that each button on IR remote has a specific code. And while making project, like you should know this code, and every IR remote will have different codes for like for individual remote. Like you cannot the generally one remote cannot control the like a remote can control a particular TV or so a particular because of these codes, because this is unique to all, or there may also be some clashes in the hexadecimal values, but generally IR remote doesn't work for the other TV other than what is yours. Generally you have like noticed it when you use a TV. Okay, so what if I remove this delay? Yeah, so yeah, so when you print it, like it prints this many times F. This means that the IR receiver is still in the code, it still has the code which corresponds to the hexadecimal value of 2. After I press 3 and keep it pressed, now it is changed to uh, the hexadecimal value of 3. And now actually it depends like when you need this and when you not need this. Like if you want some continuous, like if 3 is pressed, like if you want like continuous or discontinuous way of controlling it, like this plays a major role. You can play with if statements and like do do like you can continue or discontinue the like I just want suppose I just want like 1 to be like pressed once and nothing, it should not be carried for further, so we can use this while coding. So yeah, this much is just for simulation. Yeah, like every uh, the objective of this was to show you that every button has a different hexadecimal code. Yeah, so I hope you understood this, and uh, even if you didn't understood, you can like go through these comments that I have written. Even if you have any doubt, you can ask. Yeah, okay. So now we'll go to a project where we have to control this RGB LED, its brightness, its color using a IR remote. So before moving on, what is the RGB LED? RGB LED is just uh, a combination of 3 LEDs which has three basic colors: red, RGB. which has three basic colors R, RGB, R red, B for blue, and G for green, and it has a common cathode. So actually you can control the brightness of red, blue, and green color using the PWM. Like what PWM does is like it in the before session it was discussed that PWM controls the voltage it is received. Like what decides the brightness of a light or LED? Can you guess what decides the brightness of light and like the tube light you use, the bulb you use? Like what decides the brightness, the intensity with which it will emit that light? Any idea? Yeah, controlling the current in the sense controlling the voltage, right? So we'll connect these pins to RGB, like to this PWM pins 10, 6, and 5 to control the voltage that every color gets. And as you know that you can frame any color using red, blue, and green. We can set the different intensities and different intensities in sense 0 to 255. Like it is like the index of intensity. 255 means max intensity, 0 means it is like no intensity. And there is each for each, like this will have 0 to 255, 0 to 255, 0 to 255. So you can frame 253 multiplied by 253 multiplied by 253 colors on one single RGB LED. Okay, so what I want my remote to do is to get to print uh, to give white color when I on it. Okay, so I'll show you simulation once. I want the LED RGB LED to go off when this button is pressed. I want RGB LED to print to glow red, sorry, blue for this green and for this red. Also, I want to control the brightness of the red color. And also this is for decreasing the brightness and this is for increasing the brightness. And I also want this brightness to be retained for other pins for other when you press suppose 2, then the green also should have the similar brightness. Okay, so now we'll see the code. Okay, so I have made before seeing to the code, I have made some of the changes in code. Like I receive pin enable LED feedback. This I have added. Then these are some of the new functions which I have used. Like what I'll just go through what each does. This is like IR remote library for initializing the like to use it function in it to tell compiler that we can use the functions of this library. And we have defined this as const byte. This is like we need this syntax for fitting it here. to the function IR receive dot begin, and if I decode the IR result, the signal I received from transmitter, then it should print this. Now this is not the hexadecimal. This will be some. This is not hexadecimal. Like it will print some another value, and if like so these are the conditions I framed so that it can glow red light, it can glow white light when this is pressed, it can glow red, can glow what, it can glow no light when this is pressed, when this is pressed, I'll glow blue, when this green, and when this I'll glow red. And these are for increasing and decreasing the brightness. So since we are using PWM here, we should note that we are using analog write function and not digital write, because we need the voltages here to be off where they should be kept high, but we need some varied voltage. Like it should not give plus 5 volt. We need something other than plus 5 volt, which is done by PWM. So yeah, so I have defined this three. I've defined these three variables, which red BR stands for brightness of red, which I have initialized with 255. This stands for brightness of green, and this for brightness of blue. I'll this is the baud rate. You can set it to 9600 as well, no problem. And now this is the logic we use. Okay, so if wait, see that when I press this, I receive 0. So if I get if this after on pressing this, if I get 0, and if it matches with this if statement, this will go true, and it will set the brightness of red to 255, brightness of green to 255, and brightness of blue to 255 as well. And when I press this, it will set the brightness to it will set the brightness to 0, 0, 0. That means it has off the RGB LED. And for similarly for 1, for this on pressing 1 corresponds to 16, 2 corresponds to 17, and 3 corresponds to 18. Yeah, so this is like similar to hexadecimal. Like every button has Unicode. Like when I press this, it has 5. When I press this, it has 4. It has 6. This has 10. Okay, so yeah, so these are for this 3 if statements are respectively for red, green, and blue colors. Okay, so after this, to control brightness, if I get this command, which is for decreasing, I decrease the brightness factor. Brightness factor is the factor by which I will be reducing the brightness. So if I get this command, my brightness factor will be converted to 0.75 0.75, that is 75% of the initial brightness factor. We'll use this brightness factor here, and if I use increase, that is if I get 10, then it will increase the brightness factor by 1.3 by multiplying it by 1.3, and if it is going greater than 1, then it will keep brightness, then the brightness factor will be kept 1. So now why do we use the analog write function here? So analog write function was used is used because we are using PWM, and these are giving high values, but but these high value like correspond to like different voltages. So for 127 it will give around 2.5 volt for and in similar fashion for half of 127, that is 64, it will give some 1.25 volt. It is high, but we need to control the brightness using this. So I'll write to analog PWM pin 5 the the original brightness of red multiplied by the brightness factor, like for a LED whatever it is. It cannot go for beyond 1 and it cannot go below 0. So if you press this, it will reduce the brightness factor will become 75% of the initial, and it will be multiplied with the, suppose you have pressed 1. I'll restart this, reset this. If I press 1, and if you, then the brightness are respectively like blue, for blue it is 255, 0 and 0. Now this 0 will be not affected, like red and green, they are already 0. And for analog red 6, like which corresponds to blue pin, if I press this, then it decreases the brightness by 75%. And it is done by multiplying the value of blue, that is 255 multiplied by the brightness factor. So yeah, so in this way we control the brightness of LED. Okay, so I'll send you this code in chat. Oh, sorry. Hope the code was clear. Like you have any doubt, ask. You can just simulate it once and ask doubt if you have any. Yeah, sure. I'll send it in WhatsApp. Yeah, what does IR receive.decoded data.command do? It actually decodes the data you receive from, okay. Yeah, here it is. Oh, sorry. This is like just the command, like it see if I pressed 1, then it gave me 16. So it just like decodes the IR data and stores it in command variable. Command variable, not variable, you can say it is like used for like, no, it is not command. It is just for, it's just a syntax, like we should write this for receiving for decoding the data you receive from IR remote. And it corresponds to one value, like for 4 it is 20, for 5 it is 21. Okay, I hope it was clear to you. Yeah, any doubt, please ask. We cannot increase the brightness without decreasing it first. Yeah, because we have initialized with it with 0.255, right? 0. Sorry, 255, right? So if I do it 0 here, let's try here. Initializing it with 0, then it will print nothing. Like if even if I press something, it won't print. Oh, it's printing. Yeah, sorry, I have initialized. Yeah, okay, it will print. Sorry. Yeah, because we have initialized with it. Okay, initializing here is like not necessary, maybe. Yeah, yeah, like it depends on what you initialize here. Because for one, you will like for one, if you like for if you press one, then it initializes the red. Uh, let's okay, so let's do it here 0. Then it won't work, maybe. Yeah. Yeah, it won't work. So it depends on what you initialize here, right? After you press this, it initializes here, and you can after that you can decrease or increase, but you yeah, here you need to initialize it. You can try doing it what you told actually. If you change code a bit, you can do that. Yeah, okay. In doubts? Yeah, okay. So I hope whatever was demonstrated and spoken was uh, understandable to you. If you have any doubts, you can ask them in the Google form that will be circulated to you, and you will get your DIY task soon, and we'll soon upload the recordings and slides of this slides of day 4. I hope you enjoyed the projects and the stuff done today. And yeah, tomorrow it is holiday. We don't have session tomorrow. Yeah, okay. Hope you enjoyed the session, guys. Bye.
Guys, one more thing. The fifth session or the fifth day's week, I mean, week session will be taken on Monday rather than being conducted on tomorrow's class. I mean, tomorrow we don't have a class, so in session, we will have the session on Monday.
Like, yeah, the deadline for task, yeah, it will be communicated. Don't worry. Okay, so bye guys.